Okay, good afternoon, children. In the last class, we had discussed about the reactions of these metals and non-metals with different compounds, right? Air, then water, then metal salts, etc. Now we are going to discuss about the reactivity series. The last one, displacement reaction, we have learned that only highly reactive metals can displace lower reactive metals or lesser reactive metals. So we need to know which are the highly reactive metals and which are the lesser reactive metals, right? So there is an arrangement of metals in their decreasing order of reactivity. That is known as this reactivity series or activity series. Clear? Reactivity series or activity series. Just wait, I will show the image. So, this is clear, children? Is this visible? Yes. So, this is the arrangement of different metals in their decreasing order of reactivity. Decreasing order of reactivity. We will start with potassium, then sodium, calcium, magnesium, aluminium, zinc, iron, lead, hydrogen, copper, mercury, silver, gold. So this type of arrangement of metals in their decreasing activities, that is known as reactivity series. And this activity series is developed after the displacement reactions using these metals. From the displacement reactions, we can able to find out which are the metals that can displace the lesser reactive metals, right? So through this method, we can find out which are highly reactive, which are lesser reactive. So this is the reactivity series. Justin, can you please read the names of the elements in decreasing order of their reactivity? Yes, read it fast.
Potassium, sodium, calcium, magnesium, aluminium, zinc, iron, lead, hydrogen, copper, mercury, silver, gold.
Okay. Did you copy this order? That's also in your textbook, page number 45. So that's about the reactivity series. I will repeat it once again. Potassium, sodium, calcium, magnesium, aluminium, zinc, iron, lead, hydrogen, copper, mercury, silver, gold. This is the correct decreasing order of their reactivity towards another metals. Clear, children?
1 minute you can read.
You can copy it from the textbook. You know that within
It is a textbook.
page number 45. Within September 15th, we have to complete the portions, right? So there will be one more topic. So I need to complete it today itself. After that, we can discuss the questions. So all of you, please cooperate with me. Please switch on your videos first. I will give attendance only for those who are switch on their videos.
Ma'am, page number
45. Page number 45. So this reactivity series, you can copy it from the textbook or I will include it in the notes. No need to worry. So next, you can see there are certain questions that we can discuss tomorrow. Okay. So now we are moving to the next topic. That's about the reaction between metals and non-metals. Okay, metals and non-metals.
Can you mention once more that page
Which
number?
one?
Page number that once more.
Page number 45. Children, when you are attending any class, you have to collect your textbook, notebook along with your class. Okay. During the class time, you are going to get your textbooks. Page number 45, reactivity series is there. Okay. Now we are discussing about the reaction between metals and non-metals. So before moving to the reaction between metals and non-metals, did you heard about noble gases or inert gases?
Nobody has that as ma'am.
What is that noble gases? Which group is named as noble gases?
Carbon, oxygen and
No.
hydrogen.
helium, neon. Argon.
Very good. Which group? Which group? What's the group number?
Helium,
Anyone? Group 18. Okay. Group 18 elements are known as noble gases. Noble gases or inert gases. They are also known as inert gases. Noble gases or inert gases. They are group 18 elements. Group 18 elements. Which are they? Helium, neon, argon, xenon, krypton, etc. Okay, these are the examples of certain noble gases or inert gases. The main speciality of this group 18 elements are they are already stable. They have a completely filled configuration. So they do not involve in any chemical reactions. So these are the features or characteristics of this noble gases. They have completely filled outermost shell or completely filled configuration. They have completely filled configuration. Therefore, they are stable. They are stable. Okay. Then the third point. So they do not involve in any chemical reactions. The main purpose of involvement of elements in chemical reactions to attain the stability. So they do not take part in chemical reactions. So always you have to remember these points. Noble gases or inert gases, they have completely filled configuration. Okay. Noble gases or inert gases, they have completely filled configuration. They are stable. They do not take part in chemical reactions. We can check the electronic configuration of few of the noble gases. Okay. Starting with helium. In the case of helium, the atomic number is 2. So what about the electronic configuration? Helium. Minha, can you tell me the electronic configuration of helium? Only 2 electrons. 2 is its atomic number, so 2 electrons are there. How can we write? No idea? So you have to learn one more thing to write the electronic configuration. Okay. There are different types of shells. Okay. There are different types of shells. Which are they? Different types of shells. K shell, L shell, M shell, N shell. The maximum capacity of K shell is 2. Maximum capacity of L shell is 8. Then in the case of M shell also it's 8. N shell 18. So this is the maximum capacity of each shell. So the number of electrons present in each atom or element, we will distribute to these shells. So in the case of helium, 2 is its atomic number. That means only 2 electrons are there. So its electronic configuration is 2. Okay, it's 2. Then in the case of neon, its atomic number is 10. Okay, its atomic number is 10. So we can distribute these electrons like this. 2, 8. 2, 8. Then in the case of argon, atomic number is 18. Here we can write the electronic configuration 2, 8, 8. The total is 18, right? So in the case of this noble gases, they have completely filled outermost shell. I told you about K shell. The maximum capacity is 2, right? Maximum capacity is 2. The 2 electrons are filled in the case of helium. Then in the case of neon, you can see that 2 shells, but the 2 shells are completely filled. The maximum capacity of K shell is 2, L shell is 8. 2 electrons are filled in S shell, sorry, K shell, then 8 electrons are filled in L shell. So in the case of this argon, you can see that 288. Here also it's completely filled. So in the case of all noble gases, you have to remember they have a completely filled outermost shell or completely filled configuration. That means they are stable. They do not take part in chemical reactions. The main purpose or main intention of elements to take part in chemical reaction to attain the stability. They are already stable, so they do not take part in chemical reactions. Clear, children? So that's about noble gases or inert gases. They are group 18 elements at the right side of the periodic table, right end of the periodic table. Group 18, then they are known as noble gases or inert gases. They have a completely filled configuration. They are stable. They do not take part in chemical reaction. Then the examples are helium, neon, argon, xenon, krypton. Okay. And when you write the electronic configuration of these elements, you can observe that they have a completely filled configuration. Clear? Do you have any doubt, children, about noble gases or inert gases? Anyone? Devasena, any doubt? Yes. I can't hear you properly.
No, ma'am.
Okay, it's clear, right? So then we are moving to the reaction between metals and non-metals. So we have completed the portion of noble gases and inert gases. Then we are moving to metals and non-metals. Okay, metals and non-metals. First, we can write the electronic configuration of certain metals and non-metals. Clear, children? So in the case of metal, we can start with sodium. What about the atomic number of sodium? Delvin, can you tell me atomic number of sodium? Yes. Tell me.
Ma'am,
Yes.
ma'am, is it 1?
Then what about hydrogen?
Ma'am, 11.
Yeah, it's 11.
11.
First, you have to learn at least the atomic number of first 20 elements. Okay. First 20 elements. So in the case of the sodium, it will be 11. Then tell me, how can we write the configuration of the sodium? Anjali Priya, can you tell me?
Yes, ma'am.
Yeah. How can we write the electronic configuration? How can we distribute these electrons into different shells? You have to remember.
Yes, 8, 2.
Okay, wait. K, L, M, N. These are the 4 shells. The maximum electrons that can be accommodated in K shell, that is 2. L shell, that is 8. M shell, 8. N shell, 18. Then you can tell me what's the configuration of sodium.
Ma'am, 2, 8,
2, 8. Then
1.
1. 2, 8, 1. Right? So you have to
Yes, ma'am.
remember, in the M shell, the maximum capacity is 8. Here only 1 electron is there. That means the outermost shell is not completely filled. When we are comparing it with noble gases or inert gases, they have a completely filled configuration. The next one, magnesium. Its atomic number is 12. Eva, can you tell me the configuration of magnesium? Its atomic number 12.
Ma'am, 2,
2,
8,
8, 2, 8. 10 electrons are completed. Then 2 more electrons. So 2, 8, 2. That's it. 2, 8, 2. The maximum capacity is 8. So you can fill from 1 to 8. Here next one is aluminium. Its atomic number is 13. So Delvin, now can you tell me the electronic configuration of aluminium? Yes.
2,
2,
8,
8,
3.
3. Okay. So that's about the electronic configuration of certain metals. Here you can see the outermost shell is not completed, right? Outermost shell is not completed. So there is a chance for chemical bonding to complete their outermost shell and to complete their outer electronic configuration. Next, we are moving to the electronic configuration of certain non-metals. We will start with nitrogen. Its atomic number is 7. So how can we write the electronic configuration, Shania?
Ma'am, 2, 7.
2,
2, 5.
yeah, 2, 5. Next one, oxygen. Its atomic number is 8. Navneet, how can we write the configuration?
Ma'am, 2, 6.
2, 6. Okay. Then, sorry. It's fluorine. Its atomic number is 9. Gauri, can you tell me the configuration of fluorine?
2, 7.
2, 7. So in the case of non-metals also, the outermost shell is not completed, right? The maximum number of electrons that can accommodate in the outermost shell, in L shell, that is 8. Here you can see in the sodium 1, magnesium 2, aluminium 3, then nitrogen 5, oxygen 6, fluorine 7. So these metals and non-metals, they involved in chemical bonding to complete their outermost shell and by attaining their stability. So now we are going to discuss about the reaction between metals and non-metals. In the case of noble gases, they are already stable. They do not take part in any chemical reaction. Okay. Clear, children, about the differences between the noble gases and the metals and non-metals with their configurations? This is clear? Yes, yes. All of you, right? Srihari?
Yes,
Clear, right?
ma'am.
Yes. Raya?
Ma'am,
Yeah, tell me.
metals with full their shells completely completed, they have reactions.
Not clear
Ma'am,
once
like
again?
calcium.
Yeah, when you write the configuration of calcium, here it is 20, right? How can we distribute? 2, 8, 8. Then after that, how many electrons? 2, but it's not completed because the maximum capacity here it is 18. Okay.
Ma'am,
8.
is there any metal or non-metal with complete?
No. In the case of all metals and non-metals, they do not have a completely filled configuration. That's why they are involved in chemical bondings. Okay. Only the noble gases have completely filled configuration. Clear?
Okay, ma'am.
Okay. Then we are moving to the reaction between metals and non-metals. Okay. Metals and non-metals. We will start with the formation of sodium chloride. Write the heading, formation of sodium chloride. Then you can write along with me. Formation of sodium chloride, NaCl. Again, we can write the electronic configuration of both sodium and chlorine. Sodium, its atomic number is 11. So its configuration is 281, right? 281. The next one about chlorine. In the case of chlorine, atomic number is 17. So its configuration 287. 287. Both this sodium and chlorine, they involved in chemical reaction to complete their outermost shell. Okay. So can you tell me, children, by looking at this electronic configuration, through which way we can make the outermost shell completed in both sodium and chlorine? What's the possible way? Two types of bonding are there. First one is sharing of electrons. Second one is transfer of electrons. Sharing means each atom will share electrons. Okay. And another thing, transfer of electron. One atom will donate and other will accept. So which thing is possible here? Yeah, Shania, you can tell me.
Ma'am, 1 electron from
Hmm.
sodium, we can give that to it.
Yes. 1 electron present in the outermost shell of sodium, it will be donated to this chlorine. Srihari, same answer, right?
Yes, ma'am.
Yes. So 1 electron present in the outermost shell of sodium, it will donate it to the outermost shell of chlorine. This chlorine will accept that electron. So that type of bonding take place here. Now we can represent this in the form of a certain structure. A symbol with certain dots that is known as Lewis structure. Okay, Lewis structure. We can draw Lewis structure. Before that, we can write the chemical reaction take place in each one, metal and non-metal. Here sodium is a metal, chlorine is a non-metal, right? So first we can write the reaction take place in sodium. Sodium, it will be converted to Na plus. I told you, when someone donates something to others, it can be considered as a positive activity, right? So here also, sodium donates electron. Okay, so here sodium will attain one positive charge. So sodium will be converted to sodium ion, that is Na plus 1 electron. That's the reaction take place in the case of sodium. Okay, then we can write the configuration. Here it is 281. And when they donate 1 electron, it will become 28. 28. Okay, 28. Next one about chlorine. Chlorine will accept 1 electron and it will become Cl minus. Cl minus. So we can write the configuration. In the case of chlorine, it is 287. When they receive one more electron, it will become 288. So both the sodium ion and chlorine ion, they have a completely filled configuration in their outermost shell. So they take part in certain chemical reactions to attain this stability. So these are the two reactions take place in sodium and chlorine. This is clear, children? Do you have any doubt? If you have any doubt, you can ask me. After that, we will move to next one.
Can ma'am repeat once more?
Yes, sure. First, we write the electronic configuration of sodium and chlorine. In the case of sodium, atomic number is 11. So it is 281. Atomic number of chlorine is 17. So it is 287. So here, the only possible way to make the outermost shell complete by donating 1 electron from sodium to chlorine. Okay, then in the case of sodium and chlorine, we can write the reactions. Sodium, it will be converted to sodium ion by donating 1 electron. Na gives Na plus 1 electron. Then we rewrite the configuration. In the case of sodium, it is 281. That's the configuration. Then when it is converted to Na plus, it will lose 1 electron, right? So it is 28. Clear, Raya, about sodium?
Yes, ma'am.
Yeah. The same thing in the case of chlorine. It will accept 1 electron and become Cl minus. So first the configuration of chlorine is 287. Then when it receives 1 more electron, it will become 288. Now both the sodium ion and chloride ion, they will get completely filled configuration in their outermost shell. Okay, so this is the chemical reaction take place there. This one is known as sodium ion. And this one is chloride ion. Then one more question for you children. What is cation and what is anion?
Cation is positive and anion is negative.
Very good. Cation is positive ion, anion is negative ion. So among the sodium and chlorine, which one is the cation and which one is the anion?
Sodium is anion, cation.
Yeah, sodium is the cation and chlorine is the anion. Okay, here it is negatively charged. Here it is positively charged. No, Anjali Priya, we cannot do that because we have to fill it. After the completion of K shell, we can move to L, then M, N. Okay, correct order should be followed. We cannot able to completely fill the 18 electrons to N shell. That's not possible. Clear? Then shall I move to the Lewis structure?
Yes, ma'am.
Yes. Now we are going to draw the Lewis structure for this sodium chloride. Okay, sodium chloride. So first we will write the symbol of sodium, that is Na, right? And only represent the electron present in the outermost shell. In the case of sodium, you know that only one electron, right? Only one electron. This electron is represented in the form of a dot. This is the Lewis structure of sodium. Then it will react with chlorine, right? Chlorine. And there are 7 electrons in the outermost shell of chlorine. So we can represent the 7 electrons as into marks. 7. When these two elements, one metal and non-metal, reacts together, the sodium, it will donate 1 electron to chlorine. Okay. So the sodium chloride is formed. Na, only 1 electron present in the outermost shell of sodium, that is donated to chlorine. Then it will become Na plus. Na plus. Okay. Then the remaining chlorine. So already 7 electrons. Then 1 more electron is added from sodium. Then it will become 8. Cl minus. So this is the Lewis structure for the formation of sodium chloride from sodium and chlorine. And here you can see sodium that is positively charged, it's a cation. Chlorine is negatively charged, that's a anion. And both are oppositely charged, right? This oppositely charged charges are held together by electrostatic force of attraction. Opposite charges are held together by electrostatic force of attraction. Electrostatic force of attraction. Okay. That's about the formation of sodium chloride. Then we need to explain one more example for this formation of this type of compounds. And this type of bonding, that is known as ionic bonding. Okay, this type of bonding is known as ionic bonding. Have we completed the slide, children?
Yes, ma'am.
All of you?
Yes, ma'am.
Okay. Then this is known as ionic bonding. Ionic bonding. And these compounds in which oppositely charged, the compounds formed in the by the transfer of electrons. The compounds formed by the transfer of electrons are known as ionic compounds or electrovalent compounds. Ionic compounds or electrovalent compounds. Okay. Ionic compounds or electrovalent compounds. This ionic bonding is also known as electrovalent bonding or electrovalent bond. So we can discuss one more example for this ionic compound. That's the formation of magnesium chloride. Magnesium chloride, that is MgCl2. MgCl2. So starting with the electronic configuration of magnesium. Here it is 12. So how can we write the configuration, children? Swati, can you tell me?
2, 8, 2.
Yeah, 282. In the case of chlorine, 287. Right? But here you have to listen. There are 2 chlorine atoms. MgCl2. That means 2 chlorine atoms. So this magnesium, it will donate the 2 electrons to each chlorine atom. Okay. There are 2 chlorine atoms present in this molecule. Magnesium has 2 electrons in the outermost shell. It will donate the 2 electrons to 2 chlorine atoms. Then it will be completely filled. We can write the chemical reaction. In case of Mg, it will be converted to Mg2 plus because it donates 2 electrons, right? That's why. So we can write the configuration here. It is 282. When they donate 2 more electrons, it will become 28. Then in the case of each chlorine, it will accept 1 electron converted to Cl minus. So its configuration becomes 287. When they accept 1 electron, it is 288. After that, we can draw the Lewis structure. Have you completed this one, children? Yes or no? This is
No.
visible. Have you completed? Then we can draw the Lewis structure for this magnesium chloride. We know that in the case of magnesium, 2 electrons in the outermost shell, right? Then 2 chlorine atoms are there. We can draw 2 chlorine with 7 electrons. 1, 2, 3, 4, 5, 6, 7. Here also 1, 2, 3, 4, 5, 6, 7. So 1 electron will be donated to 1 chlorine and another to another chlorine atom. So this is the reaction take place there. Then we can draw magnesium chloride. When they donate 2 electrons, it will become Mg2 plus. Then in the case of chlorine, Cl minus. But there are 2 chlorine atoms, so we will write 2 as subscript. Okay, 2 as subscript. So this is the method of drawing Lewis structure for the formation of magnesium chloride. So which is the cation and anion present in magnesium chloride? Sean, can you tell me the cation? Yes.
Magnesium.
Yeah, it's magnesium. Very good. Mg2 plus. Then anion is Cl minus because it is negatively charged. So that's about the formation of ionic compounds or ionic bonding. Have you completed, children? Yes or no? Then one more topic remaining, that's about the properties of ionic compounds. Properties of ionic compounds. Anyone else remaining to complete this? So now we are going to discuss the properties of ionic compounds. So to learn the properties, there is one activity in your textbook, page number 48, activity 3.13. So I will read this activity and we can discuss the remaining things. Okay. Take samples of sodium chloride, potassium iodide, barium chloride, or any other salt from the Pisan, you can watch the recorded class. It's okay.
Okay.
Yes. Take samples of sodium chloride, potassium iodide, barium chloride, or any other salt from the science laboratory. So here we are mainly taking the samples, sodium chloride, potassium iodide, barium chloride. What is the physical state of the salts? Can you tell me, children? What about the physical state?
Which
What about the physical state of the salts? Sodium chloride, potassium iodide, barium chloride. They are salts. So what will be the physical state? Shania, they are salts, right?
Solid.
Solid state. Okay. They can be converted to aqueous state by dissolving water, but they are in solid state. Then take a small amount of a sample on a metal spatula and heat directly on the flame. So we are going to heat each metal salt towards the flame. Then repeat with other samples. What did you observe? Did the samples impart any color to the flame? Do these compounds melt? So you can note that in the case of sodium chloride, it will always show yellow color. Sodium chloride, it will show yellow colored flame. Okay. Then in the case of potassium iodide, violet color flame will be produced. Violet. The next one is barium chloride. Okay, barium chloride. Pink colored flame is produced. Pink colored flame is produced. That's about the observation of these three salts. Sodium chloride is yellow, potassium iodide is violet, barium chloride is pink. Then the next question, do these compounds melt? All these compounds have high melting point. So high temperature is needed to melt all the salts. They have high melting point. Then the last one, make a circuit as shown in the figure 3.8 and insert the electrodes into a solution of one salt. What did you observe? Test the other salt samples too in this manner. What is your inference about the nature of these compounds? So can you tell me, children? They are salts. When they are dissolved in water, do they produce electricity? Do this bulb glows? What's your opinion?
H plus ions is there in the water.
Yeah, here the presence of H plus ions is absent, but these can exist in the form of ions. If ions is there, they can able to produce electricity. Okay, so when the sodium chloride is dissolved in water, it will be exist in the form Na plus and Cl minus ion. Then potassium iodide, it is K plus, then I minus. Barium chloride, Ba2 plus Cl minus. So all the salts can exist in the form of ions. Okay, ions. So they will produce electricity. So based on these observations, there are general properties about the compounds. In the next page, page number 49, we will start with physical nature. Okay, physical nature. Ionic compounds, they are solids and are somewhat hard because of the strong force of attraction between them. They all are solids. You can mark it in the textbook itself, and I will include it in the notes. Okay. So physical nature, ionic compounds are solids. They are very hard because of the strong force of attraction between the atoms present in that. Okay. Then these compounds are generally brittle. We can break it into pieces when we apply pressure. When we are applying high pressure, that means we can break it into pieces. They are brittle, but they have a strong force of attraction. Then the next point about melting and boiling point, I told you ionic compounds have high melting point and high boiling point. This is the reason is that stronger inter-ionic attraction between them. That's about their melting point and boiling point. So you can mark the second one. Ionic compounds have high melting and boiling point. Then the third one about the solubility. Okay, solubility. All these salts are soluble in water. All these salts are soluble in water, but they are insoluble in petrol and kerosene. And the last point about conduction of electricity. I told you that the conduction of electricity through a solution involves the movement of charged particles. Always ions or charged particles are required for the conduction of electricity. When we are dissolving this salt in water, it will be converted into ions. Or in the melted state, not in the solid form, they cannot. Electrovalent compounds mean same, ionic compounds itself. Okay, ionic compounds otherwise known as electrovalent compounds. So here, when they are in melted state or dissolved in water, this ionic compound will be converted to ions. So these ions are responsible for the conduction of electricity in the solutions. A solution of an ionic compound in water contains ions which move to the opposite electrodes when electricity is passed through the solution. Ionic compounds in the solid state do not conduct electricity. If they are in solid state, they will not conduct electricity, but they are converted into aqueous solutions or melted state, they will produce electricity. Okay, children. So that's about the properties of ionic compounds. So we have completed our term 1 portion. Then the questions in the page number 46, 49, and the questions behind this chapter that can be discussed in tomorrow's class. Okay, the remaining portion from occurrence of metals, it's under deleted portion. Yeah, Shania. When the ionic compound is melted, it can be conduct electricity because ions are formed. That's it. If you have any doubt in this portion, you can ask me in the next class, okay? Then from the next week onwards, we will start our revision. You know that the 3 chapters are there. So we can plan the revision and conduct it in a very good manner. Okay, all of you cooperate with that. So let me take your attendance, children. Just wait. Okay, then thank you, children. See you in the next class. Okay, bye. Thank you.